So in this third part of the series on automated visual fields, we'll address the question of how do we know whether the visual field is reliable? And this is a very important piece of information in terms of assessing the visual field. And this information is provided in the red boxes that I've illustrated over here. We're going to focus on each of them. And we'll start with this one on the bottom where we have all these waves here and what they represent. So this is what's known as called gaze tracking. So this is a slide that I showed you earlier that just reminds us of what's going on during the visual field test and what the patient is seeing. We said that all these points here marked by the X are where the visual field machine needs to check the peripheral vision, and that this yellow circle here represents a light, a fixation light that the patient is looking at as a target throughout the test. And obviously, if as the test is going on, if the patient's not looking here, if there's a stimulus here and the patient's looking up here, then that's not testing their peripheral vision. The whole idea, and it's quite difficult for patients, is not to look at the stimulus. They have to be focused here the entire time. Well, how do we know if a patient's score comes out very normal, seemingly, whether they were truly looking at the target the whole time when we were testing their peripheral vision, or maybe they were just always looking around carefully for when there would be a light flashing and then they would press the button. So the machine is built in a clever way. First of all, there's a screen over here, and the screen actually, we can't see it here, but there's a camera. This light here has a camera associated with it that's taking a picture of the patient's eye. The technician running the test can actually see the eye. It's a live video, and if the patient's looking around, the technician can actually see that the patient's eye is moving around. And the technician will obviously encourage the patient to look straight ahead. But the machine does something even more clever. The machine actually tracks the amounts of eye movements of the patient. And that comes back to the graph that we were seeing in the slide. So this is the gaze tracking. Here we have over here, the x-axis is the time, the duration during which the test was occurring. And on the y-axis, we have the amounts of movement that the eye is observed to have. So for example, at this spot over here, we see that the eye is not moving very much. Whereas at this point during the test, there was a lot of movement. The eye was really found to be moving very much off target. And so this gives us an indication when we look at the results of the visual field, we look at the gaze tracking plot to get an assessment of, again, how much faith do we have in it. So which of the three here would you think is the worst? So I would hope that you would choose the middle one here, where we see a tremendous amount of movement. By the way, for those of you who want to be one-up your other knowledge of your others' friends, we see that if we here have the baseline and we have upward deflections and sometimes we have downward deflections, just so you notice the downward deflections always have basically the same amplitude, or more or less the same amplitude. Those actually corresponds to points where the patient was blinking and the gaze tracker lost the reflexes of the cornea, so that there was nothing present, no signal coming from the eye. So here, what we're seeing here is the amount of blinking that was occurring from the patient, and there's a fair amount of it. The upward deflections refer to times where the patient's eye is actually moving off the target. The machine this plot does not tell us which way it was moving up, down. It just tells us that there was a significant movement off the target corresponding to the amplitude that we're seeing. What about down here? What's going on here? Well, here the gaze tracking was not used. Sometimes it's a little difficult for the machine to pick up the patient's eye movements. It tries to decide at the beginning of the test whether it's going to be successful or not. And if the machine and the technician together feel that it's not possible for reasons that are beyond the scope of the talk, then it's just turned off and you don't see a plot. So you lose that indicator in terms of how reliable the test was. So we have these three indicators of reliability at the top left part of the printout. And the first one is fixation losses. So what the machine does is that during the test, it regularly checks to see, is the patient looking straight ahead? And it's kind of a yes or no answer. And in the case of this test, on 17 occasions, the machine checked to see was the patient looking straight ahead at the target, and found that twice the patient was not. It was looking off to the side. So 2 out of 17 times there was a problem with reliability. Overall, however, this is pretty good for patients. Most people make errors here or there. The next indicator is false positive errors. So what do we mean by that? In the case of the visual field, let's say that we have a patient who has a problem. They have a true visual field defect, but they are trying to impress everyone that everything's normal with them. Let's say, for example, that the patient has an issue and they want to drive a car, but they know they have a visual field defect, and they want to have a visual field test that shows that everything's okay and that they can drive the car, even though they certainly should not be driving the car. So their strategy is they're just going to come in and they're just going to keep pressing the clicker, because the clicker, when you press it, you're not being tested on where you saw the stimulus. It's just, did you see it or did you not? And you're not really being, no one comes and says, where did you see it? Was it really up to the right or straight ahead? So a patient might think that they can just press the clicker continuously and just keep pressing yes, 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 I see it, yes, I see it, and get away with it. And the machine's way of dealing with that is through the false positive analysis, where what happens is that at various times the machine does not present a stimulus. Maybe there's a pause, and it looks to see, did the patient press the clicker even though no stimulus was presented. So in the case of this patient, 4% of the times where no stimulus was even being presented, the patient pressed the clicker. Again, this is not bad. We would usually think that probably when you're getting above 20, 25, 30%, that that's already becoming concerning. And everyone has their own threshold. The last indicator that we're going to discuss is false negative errors. So it's kind of the opposite situation. You have someone who has probably a very, let's say, a good visual field, but the test looks horrible. And what happens here is the patient in the middle of the test just gets bored and stops paying attention and stops pressing the clicker even though they're seeing the stimulus. So how do we create a way of detecting when the patient really doesn't have vision that's that bad? So what the machine does is that at the beginning of the test, it very quickly checks, while the patient's hopefully still interested and engaged, a couple of points, and determines very carefully what the sensitivity to light is at that point. Let's say, for example, over here in our plot, just trying to get my mouse to cooperate here, that at this point here it tests and says, okay, the patient has a 27 sensitivity to light, which is pretty good. What it then does is, during the test, it comes back and shows every so often a light in that area that's even stronger than what the patient's threshold was. So it should be easy for the patient to see it. And it looks to see how many times does the patient click that they see it. And of course, if they had seen it 30 seconds ago, then they should see it 30 seconds later. And in the case of this patient, 6% of the time where that stimulus was represented to the patient, again, a stimulus that was even brighter than what the patient's threshold was, 6% of the time the patient did not indicate that they had seen the stimulus, which again is pretty good. I think any numbers that are in the single digits are very reasonable. So that's an overview of how it works. The machine actually helps us out. Let's take an example and say here that the patient instead had 10 of 17 fixation losses, or 66% of fixation losses. What the Humphrey analyzer will often do is you'll see that it'll put X's beside those values to show you that this is outside normal limits and would be considered unreliable. Okay, that's the end of the discussion on the reliability analysis for visual fields.